This is the Lab 9 at-home video, and in this video we will be dealing with a spring that oscillates on both the X and Y axis. Also, we'll have to determine the oscillation in the X and the Y direction, and determine the work done by the surroundings when we include the spring in the system. In Tracker, this is the video that we are tracking, and as you can see, this will be the spring and the mass is moving in a elliptical kind of motion, and this is the graph of the time X in terms of time. And in this tracker, I have a time frame of 98. So based off this, for my code, I would determine the total time by multiplying the number of frames times 1 over 10.5, which would give me the exact number of seconds of how much my video tracked. And then if you go over here, this demonstrates the X in terms of time, and see it's oscillating in a sine or cosine kind of function, and as expected it's oscillating between the negative and the positive. However, when you change it to the Y, as you can see, it's still oscillating, but it remains negative, and that's because you are at a negative displacement. Now when you compare this to the computational model, this is the computational model of the X based off time. As you can see, it's also oscillating between the positive and the negative. And then the red indicates the computational model, and the green oscillation indicates the actual tracker model. And so you see they are not that far off, so the error is very minor. Now when I switch to this graph, this demonstrates the oscillation, and then the Y in terms of time. So the time is on your x-axis and your y is on your y-axis. And as you can see, the red here is the oscillation of the actual computational, and the green is the oscillation of the tracker. And as well, you see that the distance and the difference between them is not that by much. So these are pretty much spot on. Now, as you can see, this is the code that I established. The gravitational constant, the spring constants which we determined, and the original L0, the relaxed length. The gravitational is the mass times the gravitational constant times the position, since we're on Earth, and the kinetic energy is just the actual ball's mass times the ball's velocity times a half times its velocity squared. And then our delta T is an arbitrary small constant so that it flows very correctly. And here's my time that we determined, like I said previously, of the frames times the 1 over 10.5. Here is my F-net gravitational, which is negative ball to mass times. And we determine our L, establishing our L hat, the vector divided by the magnitude of the length. We establish our S, the force of the spring, and the spring potential, 1/2 ks squared. And our F-net is going to be F grav plus F spring, and that's basically it. Our velocity is updated by the velocity plus the net force divided by the mass times delta T, and our position is updated as well with ball dot pos plus ball dot velocity times delta T. And as you can see, the kinetic energy is established and the change is established as well. Keep the initial and then the updated. And then here is the actual code where it tracks the new ball, like the ball of the tracker, and the top code is what it tracks for the computational model. Now the next is if we notice a difference in the oscillation period, and we did for both the actual tracker, the measured values in the computational models, you notice a difference. This is for the X oscillation, and for the computational, the X was 1.963 seconds, and the Y for the computational model was actually 1.6216. Now for the tracker, or the measured values, which is the green line right here, it was a period of 1.729 on the X and 1.554 on the Y. Now why is this so? This is so because the actual, if you see the movement of the in the tracker, if you see the movement, see how it's oscillating in an elliptical orbit where it's mostly on the, you notice more of a change in the y coordinate of it. Well, that has to do because the force of the spring and the gravitation and of the gravity is actually stronger than the actual push that Greco gives to move it along, both oscillating in the x and the y. So that's why you see that it takes longer for it to wrap around in the x rather than in the y. Now, to discuss the question about would there be any work in the surroundings? Well, the answer is there would be no work, so there'd be zero. Why is that? Is because now the spring, the mass, and the earth are all under one system. What used to be the work of the surroundings being the spring is now in the system, so now there is no surroundings affecting it, so the change in E of the system is equal to zero. Now, is the energy principle satisfied? Of course it's satisfied, because now you're just saying that E final is equal to E initial, because your gravitational is the same. What used to be your work of the spring is now included within the gravitational potential energy of the system. You still have the gravitational potential of the spring on both sides and both the kinetic energy on both sides. Now, this is the graph of the gravitational potential energy with the other energies with its original distance of negative 0.62 something, which is my original. As you can see, there's a regular oscillation. Now, when you change it to your destination, your y coordinate to 0, now this is the new graphing of the energies with the gravitational potential energy with the change in y different, where you establish the origin at 0. So as you can see, it looks very similar, but if you go back to the axes, you see right here, it's 5e to the negative 2. This is a much greater energy than the original one, which is e to the negative 4th or something close to that. What does that mean? Why was this though? This is because when you changed your origin to 0, you made the change in the y much greater. Because if you go back to the definition of potential gravitational energy, this is equal to mg delta y in Earth. Well, delta y was, when you change it to origin of 0, it goes from like 0 to negative 0.8. So what does that do? That makes your change of y much greater than when it was from negative 0.6 to negative 0.8. Changing y is much greater when you change your origin, which is why this will affect the actual energy of the system, because if you change it to 0, the total energy of the system will be larger.